Hello. Today we're going to talk about applications of the derivative. We've learned a lot about how to take many different types of derivatives using the power rule, the derivatives of the exponential function or logarithms. And now what we're going to talk about is how to find absolute and local maximums and minimums. Right? Many applications will ask us to find max and min values. Right? We might want to find the maximum profit or the minimum cost. We might want to find the maximum speed or the minimum acceleration needed for something. So if we look at the graph here on the left, two things we can notice. At the point A, if we look at that point right across, that's where we have a max. At the point A, f of A is going to be our maximum. And if we look over at the value B, f of B is going to be minimum. And one thing we notice there is that the slopes are horizontal. So one thing we can say is that f prime of A, right, our slope of the tangent line at that point is equal to 0. Likewise, for our minimum, the slope of the tangent line at that point is going to be 0. And that's not a coincidence, right? That actually gives us a definition. That given f of x, any point C we'll call a critical point, provided that the derivative is equal to 0 there, right? F prime of C is equal to 0, or it does not exist, right? This point will come more into fruition as we move on, a point where the derivative does not exist. But what we want to take from this is that a critical point is going to be any point for our function f of x where the derivative is equal to 0 there, or the derivative does not exist. Let's look at an example. Here we're given a function f of x is equal to x cubed minus 3x plus 2, and we want to find the critical points for the function f of x. And so what we want to recall is that the critical point will be any value either where our derivative is equal to 0 or our derivative will not exist. Right? Our derivative does not exist. So let's look for the first type. We'll want to take our derivative, which in this case we can just use the power rule, will be 3x squared minus 3. And we want to set this equation, our new derivative, equal to 0 and solve for x. And so when I look at something like this, when I solve for x, what I would do is I would factor this 3 out, get x squared minus 1. And I look at x squared minus 1 and notice that that's just the difference of squares, and that will factor perfectly for us. And I'll get two values, x is equal to negative 1 and x is equal to 1. So both of these points are two of my critical points. They're two possible values where I hit a max or min. And if we notice our derivative, 3x squared minus 3, this thing is considered a polynomial. And its domain, we've talked about, is all real numbers. So there is no point to fit in with number 2 where our derivative does not exist. So in fact, these two original points here, these are our critical points. So we found our critical points, but really what are they? Critical points may turn into maximum or minimum values. However, we are going to need some more information to determine what they are. We're not quite sure yet. And so what we're going to do now is talk about two categories of max and min values. Can be absolute max or absolute mins, or they could be local max or local mins. And an absolute max, f of c, is greater than or equal to f of x, right? So our point C is greater than f of x for all values of x. Likewise, an absolute min, point C, would be less than or equal to f of x for all x. Right? These are absolute, they're global maxes and mins. these are going to be points that are greater than or equal to every other f of x value, or values that are less than or equal to every other f of x value. And local max and mins are a little bit different, right? There's still going to be points for a local max where f of c is greater than or equal to f of x, but this is going to be for the x values just near c, right? They don't have to be the global or the highest point, but they have to be the highest point for its neighbors, right? For the x values around it. And we'll talk later about how we find that. And again, a local min will be the points f of c that are less than or equal to f of x for the x values near this given c value, right? And so what we're going to do is talk about exactly how to find these absolute max and mins, and later we'll discuss how to find these local max and mins. Here we have a theorem. We call this theorem the extreme value theorem because it guarantees us a spot where our absolute maxes and mins happen. And so we want to let f be continuous on a closed interval from a to b. If those two conditions are met, then f of x will have an absolute max and an absolute min on this closed interval. And the two really important pieces are that our function is continuous and we have closed bounds. And if we look at this picture right below it, we can see why we want a continuous function and closed bounds. And if we look at this, just by inspection, we can see right about here, that looks to be our absolute maximum, right? The highest point on our graph. And this point happens at a critical point. If we look by inspection for an absolute minimum, we notice our absolute minimum is going to happen there at our value b. That's our end point. So this leaves us with a little conundrum for finding absolute max and mins. There are actually two things we have to check. We have to check for critical points and we have to check for endpoints. And so the steps to finding absolute max and mins go like this. The first step, we want to find our critical points. Right? Find our critical points. We've called them lowercase c. What we want to do with our critical points is plug these c's into f of x. Right? We want to find f of c. What we also want to do is find f of a, our left endpoint, and f of b, our right endpoint. What this will do is it will tell us which of these points, f of a here, f of c, or f of b, which is the highest point and which is the lowest point. Right? And the highest y value will be our max, and the lowest y value will be our min. So let's do an example of this. Here, we want to find the absolute max and min for our function f of x is equal to 2x squared minus 4x plus 1 on the closed interval 0 to 3. Right? So our first step, we want to find our critical points. So to find our critical points, if we recall from above, we're taking our derivative. Right? Our derivative would be 4x minus 4. We set our derivative equal to 0, and we solve for x. 4x is equal to 4, x is equal to 1. Right? This is our critical point. For steps 2 and 3, recall what we want to do is find f of our critical point, f of 1. We also want to find f of 0, and we want to find f of 3, our left endpoint and our right endpoint. And what we'll do is plug that into our function. 2, 1 squared minus 4 times 1 plus 1. Right? If I simplify that, I'll get negative 1. If I plug in 0, I get 0 minus 0 plus 1. I'll get 1. And if I plug in 3, 2 times 3 squared minus 4 times 3 plus 1. And if I simplify that, I will get 7. And so for step 4, we want to look, here is our highest value. Our highest y value has an output of 7, and our lowest y value has an output of -1. And what that means for us is our absolute max will be the 0.3 comma 7, and our absolute min will be the 0.1 comma -1. The x value that corresponds with the highest y value, and the x value that corresponds to the lowest y value. Those will be our absolute max and absolute mins. Local max and mins are actually a little bit harder to find because we don't need the continuity condition. So for our local max or local min, we might have a function like we see down below on the left where our function is discontinuous. There is a break in our graph. And so what we notice by inspection, this point here we'll call D. This will be a local minimum because it is the lowest point of all of its neighbors. If I look over here to the left side, that point C, we'll label it, that will be a local max because it is the largest y value for all of the x values close to it. However, if I look, f of D, the y value for D is actually greater than the y value for C. And this poses a problem for us, right? And the problem is we cannot plug in C and D to f of x to find local maxes and mins, right? If we take the same graph, we can see we're going to need another way to determine local maxes and mins. And one thing we may notice is that our point C, which we said was a local max, what I'm going to do is if I look on the left side of C, I notice my graph is increasing. And if I look on the right side, I notice my graph is decreasing. And if I look at D, our local min, on the left side, my graph seems to be moving downward, seems to be decreasing. And on the right side, my graph is starting to rise again, so it's increasing. So what we're actually going to need to look at is we need to look at where our function is increasing and decreasing. That will tell us where we have local maxes and local mins. And that will have to wait for its own video. I hope you found this helpful, and I will see you in class.